All right. Good afternoon, everyone. Welcome. Today we're going to listen to Andy Bay, who is going to present his non-thesis poster presentation in the Department of Mechanical Engineering and Material Science. Andy, take it away. It's been such a pleasure working with you this past year and a half since having you in class, and I wish you luck. And I have been very impressed with the work that you've been doing with us. So, Andy, take it away.
All right. Thank you for coming to my presentation. My name is Andy Bay, and with the help of my advisor, Professor Della Grammaticas, I worked on the construction and simulation of a low-cost teaching and research platform for autonomous driving systems. Autonomous vehicles have received a lot of interest in these recent days throughout society, and in these recent, in these recent years, and it's been identified as a means to improve energy efficiency, transportation time, associated costs, as well as accident prevention. And so because of this, I believe teaching modules at the undergraduate and graduate level are needed to supply these skills to students in a variety of self-disciplines within the field of autonomy. In this project, it aims to identify, design, and or adapt an autonomous system that allows for the instruction of introductory to advanced concepts in this field, utilize accessible, low-cost, open source, and well-maintained communities of the practice, which cover subjects including electronics, programming, robotics, and machine learning concepts, and can be leveraged for high-impact research using blended physical and virtual design and decision-making tools. And so a multidisciplinary course to cover the basics of autonomous driving systems will be vital to train the future engineers and give them some tools to tackle this problem. My research consists of three teaching modules and two research modules. As part of the first teaching module, we will be constructing a robot for autonomous driving. In this case, I used a JetBot, which is an open source robotics platform using NVIDIA Jetson. It's very simple to construct. The chassis is completely 3D printed, and so we can revise this 3D model as well to incorporate and support multiple sensors and multiple controllers if we need. The base unit is very cost effective. The entire thing costed me less than $200. And with this lower price, we can provide opportunities for lots of people to learn more about autonomous driving systems in the comfort of their home. The JetBot and the JetSyn are also very well documented and have a growing community with lots of support. The onboard electronics are very simple with a battery powering a Jetson. And in this case, the Jetson only has one sensor, which is a camera, and it will output signals to a motor controller to drive the motors. As we build the JetBot, there will be plenty of opportunities to learn about 3D printing, basic electronics, basic Unix commands and Python, kinematics, and as we will go into, machine learning, ROS, and gazebo simulations. I will be making a website with detailed documentation on my work so others can follow along. One of the first machine learning concepts we can cover with the camera is a binary classification. In binary classification, we can have the robot recognize if an image contains a certain object or not. In this case, we will be using supervised learning techniques to train the robot. So we will be needing to collect data, and then we will have to train our model using that data, and then deploy the model onto our robot. In this case, the binary classification will check to see if the path ahead is blocked or not. In training our data, we use 200 images and we classify them. And then we split that data into two parts, a training set and a test set. And we use that to train our model. From there, we will put that model into our robot and utilize it to check to see if the path ahead is blocked or not blocked. If it's blocked, it'll just turn around, and if not, then it'll keep going straight. Another type of supervised learning we can try to do is regression analysis. Here we define a direction for the robot to follow, given a direction, so it can learn how to follow a road. So this is the same process of collecting data, training the model, and then using that model to give the robot a direction, indicated by a green circle you see on the camera. After about 200 training images, we successfully made a deep learning model where the robot can understand how to follow a track. An interesting research question that comes from this would be how we want to train our robot. There were observed differences in the robot's path based off of how we want to train it. If we look at the far right picture of the camera, where the robot is about to go on a turn, we see that we have to place our target close to the robot. Because of this, when we place our target close to the robot on straight paths, it requires a lot less training data, but it also introduces a wobbling path behavior, since the robot will try to correct itself, and in doing so, it'll overcorrect and be in the wrong direction, and we will have to correct it. We will have to correct its direction again. When we place our targets further away, however, we required more training data, since the robot had to distinguish between turn and straight path, but it allowed the robot to mitigate this wobbling behavior and go faster. But if we want to go even faster, then we can possibly use a different learning method, since this method will only have the robot learn about direction and nothing about going fast on straight paths or slowing down on curves and such. So we can use simulations to automate the learning process and use reinforcement learning so that the robot can try to go around the track as fast as possible. So we use Gazebo to simulate a world and the robot, and we use ROS to control our robot in the simulated world. We can then place our robot down and have it try to go around the track. But once it fails, which it most likely will in the first try, we let the robot know it failed, and then we place it back at the start, and using a new model, we have it go again. As we progressively train the model again and again, we can have the robot go further and further along the track. Once we get a stable robot going around the track, we can use reinforcement learning again to have it go even faster around the track. Once we get a fast-moving robot, we can actually move this model over to our physical robot, and we can adjust our model from there. In this project, I was able to simulate the environment and establish communication with ROS, but I was unable to properly receive a camera feed from Gazebo to ROS. In the future, I would like to find a better model for the road following, like using a simulation for the reinforcement learning model that I just talked about. We could also start to introduce more real-life issues like road sign detection and reacting to emergency situations. We can also add more sensors like LiDAR, IR, ultrasonic, and 3D cameras for studying other sensors and sensor fusion. And using those new sensors, we can even add SLAM capabilities to map our environment. We can also add things like microphones so that projects that other students have been working on, so we can use projects that other students have been working on for gesture and voice control on the JetBot platform. My references include papers from the American Society of Engineering Education, as well as links for Jetson project and gazebo information. Thank you for listening to my talk. Any questions?